These are third or these are second? Oh, fourth.
What?
What problem is this, third or fourth? Third.
The International Festival of Young Mathematicians in Bulgaria. They're all part of that same contest.
Right. Yeah, sure.
So we have the perpendicular bisector of AB intersects BC and the extension of AC. So let's do it like this. And points P and Q. All right. That's P, Q. M and N are the midpoints of A, B, and PQ. Okay, so we can call this M and this N. This looks like just projected geometry. Kind of feels like it. Let AB intersect CN at D. Prove that ABC and DCM have the same orthocenter. Oh wait, it already says D. So QNP infinity, if we project, maybe this will be an easy problem. I would be kind of happy if it is. So we want to show ABC and DCM have the same orthocenter, but they have the same altitude. So, I mean, really, saying they have the same orthocenter, that's basically like saying, because we know the reflection of the orthocenter over each side lies on the circumcircle, right? So basically that's just saying that if we let it meet these circles at points F and G, I think it's just saying if we reflect G over AB, that's the orthocenter of ABC, and if we reflect F over AB, wait, what am I doing here? Oh, DCM, not DCA. So all it's saying, yeah, I mean, once we know that these circles intersect on the altitude, we're done. And I feel like that probably should be easy. Let's see. Now I'm confused. Hold on a sec.
I think assuming H to be the orthocenter of ABC, I can conclude that triangle ABH is similar to triangle PQC.
So all I have to, I'm sorry, I'm just thinking something different, but all I have to show is that these two circles, if they intersect at G, then CG is perpendicular to AB. Doesn't that seem like it should be easy to prove? Yeah, so basically, let me let the circles meet at point G. Whoops. I just want to show that CG is perpendicular to AB. That seems like it has to be obvious, right? I'm just not. Today's just not my day. Well, okay, that would mean that if we projected, so are these tangent to the circles? Is C? Not necessarily. Okay, so, but basically, if we project through C, let's see. So Q and P infinity are in harmonic conjugation. So if we project, then we get A, D, B. The orthocenter, that's where the altitudes meet. We'll just type it. So
Assuming H to be the orthocenter has finished it by similar triangles.
oh, you've solved it?
Yeah.
All right. So assuming X is the orthocenter of triangle ABC.
Yeah, I see that BAH equals 90 minus B. I think you should label the point H.
All right. I'll label it. I feel like there has to be a simple way to do it using this, but
Yeah, it's just two similar triangles.
it's just similar triangles. Okay. So okay. But I feel like there has to be a way, like even without similar triangles, just showing that these circles meet on the perpendicular. Let's see. So show me your solution. So you let H be the orthocenter of ABC, right? And then
Yeah, then I am saying that angle BAH is equal to 90 minus angle B.
Okay.
Which is angle MPB.
MPB.
Yeah,
Okay.
which is equal to angle CPQ.
Okay.
We have proved one angle to be the same. Similarly, ABH is 90 minus A, which is AQM. And so triangle ABH is similar to triangle PQC.
Okay. ABH is similar to PQC. All right.
Yeah. Now, since M and N are midpoints, so MBH is also similar to NQC because they are corresponding points in the triangle.
Okay. And then it's just an
Yeah.
angle chase from there. Okay, I think I got it.
Yeah.
So All right, so yeah, we don't need these circles. I still think there might be a way without needing the similar triangles, but by using the fact that the reflection of the orthocenter over the side lies on the circumcircle. But I think this is easy enough, so I'll just write it and move on to the next problem. Yeah, thanks for the help. Okay, so I'm just going to move it over here for now. That's point D. Okay. So angle ABH equals 90 minus angle BAH or BAC. Wait, so or I'll say yeah, ABH is equal to ACH, which is equal to angle CPQ. And then we also have angle BAH is equal to angle BCH. BCH is equal to CPQ. Wait, this is CPQ, and that's, I think this should be angle CQP, because ACH, yeah. And then that means those are similar. So triangle BHA is similar to triangle QCP. And M and N are corresponding points in those two similar triangles. And so then once we know that, hold on just a second. We can find angle HMA. So angle HMA is equal to angle CNP which is equal to angle ACJ. Which is 90 minus angle CDM. And that means that MH is perpendicular to CD. And so CH is perpendicular to AB. Or I'll say implies all right, have the same orthocenter H. All right, I'm going to move on to the next problem. Thanks for that solution. Okay, this one was interesting. So K is the circumcircle of a triangle ABC. M and N are arbitrary points on CA and CB. Whoops. And MN meets the circle at U and V. And we want to show the midpoints of, did I do that right? Yeah. We want the midpoints of EM, AN, MN, and UV lie on a circle. I'm going to draw in a little bit more. It feels kind of like the Gauss line a little bit, doesn't it? So we want to show FGED as cyclic. So if we let, I'm just going to draw a Gauss line just for the heck of it. If we let AB meet UV at a point, whoops, sorry. Then we draw the midpoint of CH, and ED and I are collinear. I don't know how much that really helps. FGED. I wonder if FED is similar to ABC. This feels a lot like another problem I did on my channel where I showed that I think they might be inversely similar. So FDE 69, whoops. So close, 69 degrees and 68 degrees. Let's see. Maybe GD is similar. So, although I don't think so. No, I don't think either of those are similar. Let me get rid of the Gauss line. I don't think that does too much. But maybe the gliding principle will help. Let me draw the center of ABC. Yeah, I'm trying to remember that other problem on my channel. But yeah, I know I had another problem where I have like both of those midpoints like this. I mean, if we label the midpoint of AB, then OH is perpendicular to it, and these are both parallel, right? Let me just draw the circle just for the heck of it. Are those tangent to the circle? see. I don't think so. No. So, but we also have OG is perpendicular to UV. Yeah, there's a lot of flexibility here. M and N can be any points. Let me do this. So if I draw this, then MIN is similar to IAB, and F is the midpoint of MN, and H. But they're directly similar. They're not inversely similar. So you know what I could do? I could reflect I across MN and then try to use the gliding principle. So IMN is similar to IAB. Oh, does I prime lie on this circle? Or is that a coincidence? Oh, it's a coincidence, yeah. Okay. But basically, okay, so basically I'm saying, okay, if we draw the altitude from I to MN, then I can show, which is basically the midpoint, is it? Or not necessarily, but if we draw the altitude from I, it's hard to get a good picture here. If we draw this point right there, J, then I can show JDE is similar to IMN, which is similar to IAB. Is that right? Actually, no, that doesn't look true. Oh, because then they wouldn't be oriented similarly. Yeah, so I can't do that. Let me hide some stuff. Maybe I'll draw this in later, but. All right. So how are we going to show that that's cyclic? see. So that's 60.7. Oh, so yeah, EFD. It looks like angle EFD is equal to angle ACB. I know I did this on my channel before, right? This is I definitely did this on my channel.
That's obvious, maybe because FE is parallel to CA and FD should be parallel to BC.
Oh, it's really that easy. Okay. Wait, so yeah. No, but I think on my channel I showed that maybe EGD is also equal to that. So EFD is trivial because they're both parallel, right? Like you mentioned. I didn't see that. But EGD, I think I might have done that on my channel. Let me look at on my YouTube channel for a sec. Let's see, hold on. I'm gonna look at it in a different window. Whoops, sorry. You guys still see the screen, right? So if I look at my past videos, whoops, sorry. How do I mute this? Here we go. Oh, I showed if, oh, and the problem on my channel that I did, this line MN has to pass through O. And then I showed, hold on one sec, what did I do? Oh, I showed that if O is the circumcenter and M and N pass through O, then I showed it's true. So if M and N pass through O, then I showed that the problem is true. So yeah, basically I proved it in that special case when M and N passes through O. And that wasn't an easy proof to do, but I used the gliding principle. So now we want to do it when M and N don't pass through O. I wonder though.
Excuse me, I think I've got a solution, but that does not include the points I, etc.
Say that one more time.
I have got a solution, but that uses the orthocenter of MCN and
Okay.
the diameter CX. Let X be the antipode of C.
Okay. So I'll let X be this point.
Yeah. And let R be the orthocenter of CMN.
Okay. All right.
Yeah. Now I claim that the midpoint of Rx also lies on this circle.
Okay.
Yeah. Now I prove that. Now I assume that midpoint of Rx is J, and then prove that JF is the diameter of this circle.
Hmm.
Means I individually prove all of them 90 degree.
Okay.
Yeah, so we observe that since XA and RN and XA are both perpendicular to AC.
Okay. They're parallel.
And since E and J are midpoints of A and XR, hence EJ should also be parallel to them. Yeah, because both of them are midpoints of the diagonals of this.
Okay.
So EJ has to be perpendicular to AC.
Okay. So you're saying BJ is perpendicular to AC and AJ.
None EJ.
EJ?
Not yeah, EJ. Yeah, this because both of them are midpoints.
Okay.
And now we know that FE is parallel to AC because F is the midpoint of MN and E is the midpoint of AM.
So yeah, FE is parallel to AC and FD is parallel to BC, right?
Yeah, this implies that both angle FEJ and FDJ are 90 degree.
Okay. And then
Now we prove that J lies on the perpendicular bisector of UV.
okay. Hold on just a sec.
I think we have many extra points there.
All right. So you used R. I'm just trying to think. It's interesting. All right. So
Yeah, and JOG are collinear because JO is parallel to AR, which is perpendicular to UV. Because J and O are the mid.
Okay, so JO is parallel to AR. Okay.
CR.
I'm sorry, yeah, JO is parallel to CR. Okay. Let me type up a bunch of stuff here. Okay, so okay. So we don't need point I, we don't need this circle.
We don't need H.
We don't need H.
And we don't need, yeah, we need over here.
Yeah, okay. So
We started with R as the orthocenter and CX as the diameter. CMN.
all right. And then you say let J be the midpoint of Rx, right?
Yeah.
All right. And then how do we show, okay, so first I can show FE is parallel to the AC and FD is parallel to BC.
Yeah. Now we know that since R is the orthocenter, hence RN is perpendicular to AC.
Okay, so RN is perpendicular to AC.
And AX is also perpendicular to AC because XC is the diameter.
Okay, so that means that Rn is parallel to AX, right?
Yeah.
Okay.
And since Rn is parallel to AX, the line passing through midpoint of both of these segments means Rx and An. This also is parallel to both of them.
Okay. So
This means
yeah, okay, I see what you're saying. So J is the midpoint of Rx, and E is the midpoint of AN. That means that EJ is perpendicular to AC. Okay. And then similarly, DJ is perpendicular to BC. All right. And so also, and then we have the parallels, like you mentioned. So EF is parallel to AC. Since EF is a mid-segment of triangle AMN. So that means EF is parallel to EJ. I'm sorry, EF is perpendicular to EJ. All right. And so that means that PFEJ is cyclic. And then how did we show D lies on that circle?
We see that JO is parallel to CR because both of them are midpoints.
So triangle CRX. And then so that means that JO is perpendicular to UV. And then so JO and G. So that means angle JGF is equal to 90. And that solves the problem.
Yeah.
It's amazing that you figured this out that fast. I'm really impressed. Wow. All right. This is a really awesome solution. So I will move on to the next one. Let me just draw on that circle just to show what we're proving. Very, very cool. All right. So, oh, this one was really interesting. I'm glad we got to this. So we have a triangle ABC with in the center I, and let A1, B1, and C1 be the points of tangency. Okay, so this is A1, B1, and C1. So yeah, I looked at this problem really briefly, but I didn't spend any time solving it really. So we want to show that these three circles, AI A1, BI B1, and CI C1 meet at another point. So you can see it in the corner. Yeah, so kind of like this. All right. But yeah, it's really impossible to draw it without the circles being really big. But yeah. All right. So how do we? Can we say some special property about that point? Maybe it lies on some other circle. Maybe we could let two of them intersect and we could try to show it lies on the third circle. I guess there's a couple different ways we could do it. So if we try to do it that way, like we said, D is the intersection of those two, and then we try to show that yeah, what if we let, yeah, probably, yeah, so I'll draw the intersection of the B and C circles and then try to show it lies on the A circle. Okay, so you have I, so that's an angle bisector. Whoops. All right. So how should we do it? What angles should we look at? Should we use power of a point? Oh, what about the power ratio lemma? Maybe that just makes it really easy. I'm trying to think. We want to show that the ratios of the powers of A and A1 with respect to those two circles are the same. So I don't think, yeah, they're not tangent to BC. So what's the ratio of the powers of A with respect to both circles?
I think I have a simple standard solution for this one.
Okay.
That we consider the diametrically opposite point of I in all the three circles.
Okay.
Which simply means construct a perpendicular at IB. At B.
Okay. So you said that the diametrically opposite point of I?
Yeah, in all the three, I would show that the centers of the three are collinear.
Okay. All right. So
Now I am assuming that circumcircle of A1.
okay. So
Yeah, I am not considering the point D initially because
okay.
it follows directly if I prove the centers collinear.
Okay. So
Yeah,
basically, now I see what you're saying. So I will try to draw those 3 points.
HJ, and the last one should be collinear with HJ. That follows directly from external angle bisector theorem.
All right. So if I draw those 3, basically you're saying L, H, and J are collinear with D.
No, I am not saying that they are collinear with D. I am just saying that LHG are LHJ are collinear.
L, H, and J are collinear. Okay. So,
Yeah.
so we have that L, H, and J are collinear.
Yeah, this follows directly from Mathematicians theorem because H lies on AC and L lies on BC.
Okay.
Yeah, that follows from the definition of angle bisector.
Okay.
And
or
by
maybe
Mathematicians,
it's the trilinear. Well, yeah. I mean, basically, we can apply. Is it Desargues theorem or something? Let's see.
maybe we can apply that, but we have all the ratios here. We know that by Mathematicians theorem, LHJ are collinear.
Okay, so we can use Menelaus.
Yeah, and we know that they are the angle bisectors, external angle bisectors.
I wonder if we can also use Desargues theorem. That might be, yeah,
Might
because
be more.
let me just think about this for a second. So IB, IC, and IB1. Oh no, that's not IB1. Yeah, I'm wondering if there's like a way without calculation where we could just like see, because I feel like this looks kind of familiar.
And that's not that much calculation, though angle bisector theorem gives the ratios directly. But here the basic point is to prove LHJ collinear, which implies that the midpoints of these segments K, E, and F are collinear.
Okay. That would mean K, E, and F are collinear.
Yeah, because these are the midpoints of IL, IH, and IJ.
Okay. And then
And this implies that the centers are collinear, hence they have to be concurrent on some other point.
Okay. So hold on a second. This looks a lot like I see because since the centers of all 3 are collinear, they all pass through I, they have to concur at another point by symmetry.
Yeah.
Okay. Let me think. So yeah, I wonder. Yeah. So you said it kind of follows just from the angle bisector theorem that LH and J are collinear, right?
Yeah, we can also define H to be the point where external bisector of angle B meets AC.
Okay. So
Because angle IBH is 90, hence we know that that angle is bisected.
okay. And then so we're gonna find H like that. Okay, so yeah, basically it follows from the angle bisector theorem, because H, it's where the angle bisector B meets JL. And okay, so, all right, so I'm going to write this up. Okay. All right. So let IL and IJ be diameters of all right. And then let the circle BIB1 meet JL at point H. So I'm just gonna, yeah. All right. And then we know that, yeah, how do we show that H is the antipode of I? So I know BI bisects angle ABC. How do we show that BH bisects angle JBL? Or is that obvious? See what I'm saying? Or we could just let H be where the external angle bisector meets. Yeah, okay. So I'll instead write it like this. So let the bisector of JBL meet JL at H. Okay, so I'm going to do it that way instead. And then, okay, so then we have angle IBH is 90 degrees. How do you know that angle IB1H is 90 degrees? Oh, I think it's better to do it the other way, actually. So, or you kind of see what I'm saying? Oh, are you still there? Sorry.
Yeah.
So how do I show, like, how do you want to define H? Do you want it to be where the circle meets LJ, or do you want it to be where the angle bisector meets LJ?
Angle bisector meets AC.
Oh, meets AC. Okay. All right.
Yeah, and then I can prove that they are concyclic.
Okay.
If they are concyclic because IBH is IB1H, both are 90.
Okay. So all right. And so then we can draw that circle. And then from there you can show that J, H, and L are collinear. How do you show that?
I used Malenius theorem for this.
Menelaus theorem. Okay. So
We write the ratios LB by LC, HC by HA, and JB by JA. I mean, in
okay.
some cyclic order that all of them would cancel because of angle bisector theorem,
Okay.
and hence they would be collinear.
All right. Let me think about this a little bit. Trying to think. Maybe we could use Monge's theorem. So yeah, I'm just trying to see if like you can use Desargues or something. Hold on. No, L doesn't lie on the polar bay. All right. I'm just going to write it out quickly since I'm just going to say by an argument using Menelaus' theorem, LH and J are collinear. Right. And then KEF is a midline in triangle IJL. So that means that KE and F are collinear. And then once we know that, so then the reflection of I over line KEF passes through all three circles. All right. That was another awesome quick solve. We have one more problem left. Let's see how far we can get before we finish. All right. Oh, this one looks interesting. So we have a circumscribed quadrilateral. Just trying to draw this as fast as possible. So they're saying the center's I. We want this to be point B. All right. C. Okay. So we have a circumscribed quadrilateral. DA intersects BC at a certain point. So DA intersects BC and AB intersects CD. Okay. Something like this. Let's see. Like that. Draw these points. Whoops. There we go. E and F. And then the in-circle of, wait, so we have A, B, C, D. DA intersects BC. This should be E, and that should be F. And we have 3 minutes left. Let's see how far we can get. So in circle of EAF. Whoops. Wait. DA intersects CB at E. That sounds right. Oh, you know what? Let me swap these. So let me make that A, this B, and so this looks better. All right. So in circle of EAF. In circle of ECF. I think it should be FAD, the midpoint of AC. We want to show lies on the radical axis. All right, I don't think we're going to solve this in time, but it's interesting. Are those circles the same size? E. So wait, did I even do the problem right? So we have a ABCD. DA intersects CB at E. AB intersects CD at F. We draw those two in circles.
I think there are some cyclic things here like FDGB.
So you think there's some cyclic quadrilaterals like FGE?
FGDB.
FGDB. Okay. Almost.
EGDC or something like
that. Interesting. BGIE and B.
No, I does not look like it's on that circle.
Yeah. All right. Well, we're out of time today, but thanks a lot for attending, and you were awesome today. I was not too with it, but you like just ran right through all the problems, so that was amazing. So thanks a lot.
See you next time.
All right. See you next time.